10.3 is going to be a relatively quick section of the book. It has a key idea that you need to practice and sort of integrate with your thinking, but it's a pretty foundational idea. It won't be hard to get the hang of it. As long as you practice a couple of key tricky issues, you should be okay. The key idea here has to do with the rule for what to do when you multiply two roots together. And it's a really simple rule, like you can see here, that if you have a product of two roots, you can make one root out of it. Realistically, though, that's not a very practical thing to do. You will see a couple of homework problems that have you do that kind of thing, but honestly, it's very, very simple. Most of the time, what you have to do is go backwards, starting from a single root and breaking it up into two roots. And that might not seem like a good idea until we work a few examples. You'll see why this is considered simplifying and how important it is. So here are several examples. I'll work left to right. The one on the left, the issue I want to show you here is that you can break 50 up a bunch of different ways. For example, you could break up 50 as 5 times 10, and then the rule we were just talking about, if you use it in reverse, you can break that up into the square root of 5 times the square root of 10. But that's kind of a dead end. That isn't any simpler than the root we started with, and in a sense it's more complicated because you've got two roots where there used to be one root. But amongst the different ways that you can break up 50, one of the ways is pretty useful. If you break up 50 as 25 times 2, think about what happens when you make that into two different roots. One of those roots can be simplified. Square root of 25 is just 5. And that is a simpler problem, or a simpler expression, than the one we started with. Square root of 50 is a square root of a fairly large number. The only square root we have now is the square root of 2, which is a much smaller number. So this is considered a simpler form than the thing we started with. So with that in mind, if that's the concept of what we're trying to do, we're trying to take the number inside the root, break it up as a product, where part of the product can be actually worked out, then let's take a look at square root of 48 and keep that in mind. Now I'm going to do this sort of a slow way and then a fast way. The slow way, sort of the natural way that most students at first would think of, would look at 48 and they'd see that there'd be a 4 in there. Especially if they're thinking, I want to take a square root, I'm thinking of a perfect square. It's real obvious that 48 has 4 in it, and it's real obvious that 4 has a nice square root. I mean, it's one of the easiest square roots, isn't it? But remember, whenever you're simplifying problems, you're expected to simplify as far as possible, and that's not fully simplified. The reason it's not fully simplified is because 12 can be broken up too. And the square root of 4 that's there also can be taken simplified to 2. So the rule is, just like it always has been with any simplifying ever in math class, simplify as far as possible. Don't just simplify a little bit and stop. Always simplify as far as possible. Now, if you're better at this, if you've practiced more and you think more broadly about possibilities, you might have been able to do this problem faster. 48 can be broken up as 4 times 12, but it could also be broken up as 16 times 3. That's not as obvious. You really have to know your multiples of 3 and your multiples of 16 to recognize that. But you can see that's going to get us to our answer a little quicker. Only one step, basically, instead of 2 steps. One breaking up, one root worked out rather than 2 roots worked out. And of course it leads to the same answer when we're all done. This rule will also apply to roots that are not square roots, like our next example here, cube root of 40. And the key thing here is you've got to break your mental habit of thinking of perfect squares all the time. You don't have as much practice with other exponents, so you don't instantly think of cubes and 4th powers and 5th powers. Your mind has sort of instinctively been programmed to think about squares. So a sort of a new student that doesn't completely know what they're doing here might think that this is a reasonable way to break up this problem. But if you think about it for a second, the cube root of 4 is not the square root of 4. It's a different type of root, and it doesn't work out particularly nice. That's a dead end. So instead of trying to break things up as squares, 2 squared is 4, what you should be thinking about is you should be thinking about cubes. So if it helps, you can make a little cheat sheet of some perfect cubes so you know what kinds of things you're looking for. And how long do you continue this list? I don't know. It totally depends on the problem you're working on and how far you feel comfortable doing it. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, etc., etc., etc. And what you're trying to do is break 40 up into 2 numbers where one of the numbers is in that list. And I think it's kind of obvious. 40 can be broken up as 8 times 5. And then the cube root of 8 is the part that's going to work out nice. Cube root of 8 comes out to be 2. And we have a smaller root. Instead of cube root of 40, the root part is simplified down to cube root of 5. A smaller, simpler root. Has a coefficient on it too now, but that's not a problem. You also are expected to do this with variables. Like here, we've got square root of 6x squared. And the problem here isn't breaking the numbers in 2 parts or something like that, but it's a little more direct. It's already kind of broken up for us. And the square root of 6 is just going to be the square root of 6. It's not going to simplify any. But the square root of x squared obviously simplifies. Please remember back in 10.1 that when you take the square root of x squared, it doesn't quite cancel the way you'd like it to cancel. You'd like to say it's just x. But unfortunately, remember, if you try negative numbers in there, you actually end up with a positive result. So the square root of x squared, and this works for all even exponents, its absolute value of x. Of course, sometimes the directions will tell you to do something different. If the directions say something like, assume variables represent positive quantities. Let's say the directions say that. Assume variables represent positive quantities. If the directions say something like that, then your square root of x squared will simplify the way you'd like it to. You have square root of 6 and then x. But then there's another issue, and the other issue here is that depending on how you write on paper, it's kind of questionable what you meant here. You know, did you mean that to be square root of 6x or square root of 6x? You know, it really depends on how far you write that line. If your line goes like a couple of millimeters further, all of a sudden the x is inside the root, and it's not supposed to be inside the root. It's supposed to be outside the root. So we encourage you, and it's kind of considered proper form, to put all the non-root parts first and all the root parts second, so that there's no question what's inside the root, what's outside the root. The x is clearly outside the root, and it doesn't matter how far you drag your pencil on the top of that root symbol. Most of the homework problems you're going to see in 10.3 are going to be kind of larger, more complicated versions of that problem we just did there. They'll tend to be problems like these ones here. And these two are very similar problems. In fact, really the only difference is the one on the left is a square root, the one on the right is a cube root. But aside from that, they've got the same expression on the inside, 54x cubed y to the 4th. So what I'm trying to illustrate here is, first of all, what kinds of problems do you actually need to be able to do? And how do they vary when you've got different roots? So for the one on the left, we should be thinking in terms of squares, perfect squares. 4, 9, 16, 25, things like that. Those are perfect squares. So when we're looking at 54, we should be asking ourselves, does 4 or 9 or 16 or 25, does a perfect square go into that? And the biggest perfect square that goes into 54 is 9. It's 9 times 6. And I'm going to break it up really far apart like this because several things are going to end up coming out of this root. And I'm going to put them all on the left so that when I'm done taking the roots, they'll be sitting in front of the root like they're supposed to. And there will be a few things left over inside the root, and I'm going to put those all on the right where that 6 is, and so that way all the stuff inside the root will be on the right when we're done. Next, look at the x's. X cubed. Is there something squared inside of x cubed? Yeah, of course. There's an x squared inside of x cubed. X cubed breaks up as x squared times x. So I put the two pieces, one on the left, one on the right. The one on the left will come out of the root. The one on the right will sort of be left over. And then the y to the fourth will already have a nice square root. I don't have to break it into two pieces. If I broke it into two pieces, both of the pieces would come out. It would be kind of silly to break it up. And then you go through and you do the root of these three in the front, because each one of those has a nice root. And on the right, this stuff is kind of like the leftovers, the residue. It won't have a nice root. But square root of 9, that has a nice root. That's 3. Square root of x squared, watch out, we just talked about this in the previous problem. The square root of x squared is the absolute value of x. And then the square root of y to the fourth is kind of an interesting case. I don't need to put absolute values on there. And I'm sure that that was like your first instinct because of me making a big deal about it. So the question there is, why not? Why not absolute value of y squared? And here's the reason why. This is a simplification type of an issue. Could y squared come out negative? Well, it's squared. It can't come out negative. So what would be the point of saying absolute value of something that's already going to be positive no matter what? So the reason why you don't put absolute value on y squared is because y squared, it's already going to be positive. Putting absolute values on it would be a waste of time. It's, simplest form. Don't put something there that you don't have to put. So yes, whenever you cancel even roots, you get an absolute value, but still, don't just think of that robotically. Think about what the absolute value is supposed to do and why you might need it, and you realize you don't need it there. Now this other one over here, this is cube root stuff. So you got to sort of reset your mind. Don't be thinking about perfect squares. Think about perfect cubes. Things like 2 cubed, which is 8, 3 cubed, which is 27, 4 cubed, which is 64, and so on. What of those goes into 54? Well, it's 27 times 2. The cube root of 27 is going to be 3. X cubed is already going to cancel with cube root. And remember, with odd roots, you don't get the absolute value thing. And then y to the fourth has to be broken up, y cubed and y. Y cubed has a nice cube root. And our residue this time is cube root of 2y. Those are the pieces that don't come out of the root. So notice how these come out different in the way you go through them. Although it's kind of superficially the same, the details are different because square root versus cube root. Those have some pretty significant differences. And you should also be imagining how this would be different if it was, say, fourth roots or fifth roots. Similar kinds of ideas, breaking things up based on the exponent you're dealing with.